In this presentation, I would like to continue our discussion about shear force and bending moments. We will try to learn how to draw shear force and bending moment diagrams from first principle and using graphical approach. Please note that shear force and bending moments in the literature are symbolically referred to as V and M respectively. So if we use P and M in this presentation, then please be aware that we are referring to shear force and bending moments. The variation of shear force and bending moment over the length of a beam provides information necessary for the design analysis of the beam. We have already discussed in our previous presentation that in the case of beams that are subjected to loading which are perpendicular to the longitudinal axis of the beams, the internal effects essentially developed within the beam are shear forces and bending moments. That's why we are interested in finding out the variation of these shear force and bending moment as we move along the length of the beam. In particular, the maximum magnitude of bending moment is usually the primary consideration in the design or selection of a beam, and its value and position should be determined. The variations in shear and moment are best shown graphically, and the expression for V and M when plotted against the distance along the beam give us the shear force and bending moment diagram for the beam. So if we have beam subjected to some loading, we can determine the internal effects, that is shear force and bending moment, using a graphical approach. Or thus, if we have got a beam subjected to some loading, its internal effects could be found by drawing bending moments and shear force diagrams. Unlike the axial stresses and strain case, where we had a load applied only at one point and the stresses or strains were constant in the structure, in the current case where the load is applied vertically, there is variation in the internal effects. Therefore, we need to know how the shear force and bending moments are varying as we move along the beam. In order to draw the shear force and bending moment diagram, the first step is to determine all the external reaction on the beam by applying the equation of equilibrium to a free body diagram of the beam as a whole. As we can see, the beam subject to some loading. Next, we isolate the portion of a beam either to the left or to the right of an arbitrary transverse section with a free body diagram and apply the equation of equilibrium to this isolated portion of the beam. These equations will yield the shear force and bending moment acting at the cut section on the part of the beam isolated. The part of the beam which involves the smaller number of forces either to the right or to the left of the arbitrary section usually yields the simpler solution. Although we have said that we can take a section either to the left or right of the beam, but it is better to be consistent and just to set out one type of methodology and sign conventions. Thus, we would isolate a portion of the beam that is to the left of an arbitrary transverse section. We will assume that the load is positive if it is facing upwards. The shear force at an arbitrary transverse section, if facing down, would be treated as positive. And similarly, the counterclockwise moment at the arbitrary transverse section will be treated as positive. It is important to note that we would not take a transverse section which coincides with the location of a concentrated load. So in the case of a beam subjected to concentrated load, we will normally take the arbitrary transverse section to the left or to the right of the applied concentrated load or concentrated couple. Please note that the concentrated load or a concentrated couple will represent a point of discontinuity in the variation of shear force and bending moments. Just to reiterate finally that the calculations for the shear and moment on each section chosen would be consistent with our positive sign convention illustrated in this figure. Now let us do some examples in order to clarify whatever we have said so far. So we will start with drawing bending moment and shear force diagram using first principle. So in this example, we have got a uniformly distributed load having magnitude W per unit length, and the beam which is taking this load is of length L and is supported simply or is simply supported. So as we said, the first step in determining bending moment and shear force diagram is to work out the support reaction. We will take moment about the supports in order to determine the unknown reactions. So in other words, we will make use of equilibrium to work out the reactions. After finding out reactions, we will isolate the portion of the beam that is located towards the left of the arbitrary chosen section. The left portion of the beam is starting from point A, and we take an arbitrary transverse section which is located at a distance x from the left support. Now we'll apply two equations of equilibrium, which is summation of forces in y direction must be equal to 0 and summation of moment must be equal to 0. Please note, as we discussed, we will take the load facing up as positive. Hence, summation of moment about y equal to 0 and the loads which are facing up are considered positive. As per our convention, we will apply an arbitrary shear and moment at our reference section. The shear and moments applied are positive as per our sign convention. So WL by 2, which is facing up, is taken as positive. The uniformly distributed load is of magnitude W. So the total load on our arbitrary section is W times X, and that is facing down. Similarly, the shear V is facing down. From this, we will get an equation which is of first degree. This is equation of a straight line. Now applying summation of moment equal to 0, considering that counterclockwise moment is positive. In this regard, the moment caused by the reaction WL by 2 is negative because that's clockwise. So WL by 2 times X. Then the moment caused by the uniformly distributed load W times X is counterclockwise at the arbitrary transverse section. So Wx times X by 2. Please note Wx will be located in the middle of our free body and X by 2 is the lever arm. After this, the internal moment will come, which is M in counterclockwise direction. From this, we get M is equal to W by 2 small bracket Lx minus X square. Please note, our applied load was of 0 degree. The shear is 1 degree up, i.e. it is of first degree. It's a straight line which has got slope. W has got slope of 0. Then the moment is 1 degree up compared to the shear, and it is parabolic. The reason we have to be particular about the degree of the curve is because we have to draw it correctly. Now we have got the beam having the load W and the reactions. In order to draw shear force, we say that at point A, the shear force is WL by 2 because x is 0 at point A. At x is equal to L by 2, we have shear 0. Thus, at x is equal to L by 2, the shear force come down to 0. After this, the shear becomes negative as per our sign convention. So as we can see, we have got a straight line which has got some slope, and we call this line as a first degree. Similarly, we can draw the moment diagram as in accordance with our equation. At x is equal to 0, our moment is 0. So the moment will start right from 0 point at the left support. We can put the value x is equal to L by 2 and get our maximum moment whose magnitude is WL square by 8. From point